we're excited tonight to learn more about the God particle. Okay, so and we have Brian Southworth from Eckerd College, the Aspect Group. We're fortunate to have him here. He's an expert on particle physics, because I have the comic book. He actually, when you can actually explain particle physics and put it into a comic book, you know the subject. Okay, so all right. So Brian is part of the Aspect Group, but he spent most of his career in the CERN laboratory, where the Higgs particle that we'll be hearing about tonight was discovered. For many years, he was the editor of the International Journal of High Energy Physics, and also founded the Journal of European Physical Society. Brian is happy to be with us here tonight. He has set up many science exhibits and exhibitions throughout Europe, including the Science Pavilion at the 1992 World Fair in Spain. World's Fair in Spain. So we're fortunate to have him here with us tonight. So thank you, and we're looking forward to becoming a lot smarter in physics.
Thank you, Joe. The 4th of July 1976 was, of course, a very important day in American history. The 4th of July 2012 was a very important day in science history, because it was on that day that 2 teams of experimenters at the CERN laboratory in Geneva, Switzerland, announced that they had found convincing evidence of a mysterious particle called the Higgs Boson, which is so important in our understanding of how nature behaves that it earned the name of God particle in a book about it by Leon Lederman, who was at that time the director of Fermilab near Chicago. Leon I always introduce as Nobel Prize winner and comedian, because he has a joke for every occasion, and he pretended that he'd sent along to his publisher the title "The Goddamn Particle," because it had been so elusive. It had been predicted 50 years previously and not found, and it had been so fiendishly expensive to find. His publisher refused to accept Goddamn particle. The seemingly complicated business of particle physics is in fact trying to find the answers to 2 what seem quite simple questions. What are the basic building blocks, the Lego blocks, if you like, from which everything is constructed in our universe? And then, what is it that controls how those Lego blocks behave in order to produce the universe that we see around us? The ancient Greeks had the idea that the 4 elements of fire, earth, air and water were all that we needed. Of course they were wrong, but they did also have the wonderful idea that you could not go on breaking up matter forever, slicing it into smaller and smaller pieces. Otherwise you'd finish up with nothing. And they chose the word atom, which means indivisible in Greece, for the smallest pieces that you could possibly have. They seem to be spot on when in the 19th century the chemists discovered oxygen, nitrogen, hydrogen, etc., and eventually produced what probably many of you met in your school days, the chemical periodic table. Using these elements, you could, in principle, produce anything in the universe. Here's the supposing, for example, we wanted to produce salt. Then we would need an atom of sodium, and we would need an atom of chlorine, and we would have our salt. So maybe this was the answer. These were the basic building blocks of matter. At the end of that century, we discovered that tiny pieces could be pulled out of atoms. So atoms were not the answer. Those tiny pieces we call electrons. They carry a single electric charge, negative electric charge. In 1912, a physicist by the name of Ernest Rutherford fired energetic particles at a thin gold foil, and from the way they bounced off, he realized that at the center of the atoms was a tiny, very solid core. I'm sorry, am I cutting you off? Can you hear me?
Yes.
He said it was as astonishing as if I'd fired a shell at a piece of tissue paper and it had bounced back and hit me. So this is our familiar picture by now of the atom. The solid core surrounded by a cloud of electrons. Fairly rapidly, it was found that there are two types of particle inside the atomic nucleus. We call them proton, which carries a single positive charge, and neutron, which is electrically neutral. A big change came when we developed the technology to build particle accelerators and further down the line particle colliders. Because this, for the first time, gave us access to higher energy environments that we had experienced before and under controlled conditions. When we started operating these accelerators, we were astonished to find that at higher energies, a whole zoo of new particles appeared, in addition to our proton, our neutron, and our electron. And eventually, let me intervene here just because I'm going to start using some measurements, units of measurement, that you probably won't be familiar with. It's just as if you were measuring length, you could use inches or you could use centimeters, etc. We find it convenient when we're measuring energies to talk about the electron volt. And here we have a little picture of if we had a 1.5 volt battery and we tied metal rings to each pole, a singly charged particle passing through would gather an energy of 1.5 electron volts. So that's our new measurement of energy. We talk about electron volts, EV, million electron volts, MeV, 1,000 million, GeV, and now the energies we have in our new collider, million electron volts, TeV. We can also, this is just a tiny bit of mathematics, don't all run away. From Einstein's equation, famous equation, E equals mc squared, which is really telling us that energy and matter are the same thing and are interchangeable. We can convert energy into matter and matter into energy. We can also use EV as our measurements for mass, because we can play with this equation. E and mass is equal to E over c squared. We've said we're going to use EV for our measurements of energy. So therefore a mass, for example, of 125 GeV, which is the mass of the Higgs boson, we can call it what we can use that instead of any other units for the mass. So again, we're using EV, and normally we just ignore this c squared at the end. So this zoo of particles that we discovered at the accelerators, we eventually found could be explained if they were built of 3 different kinds of particles that we gave the weird name of quarks. So if we had 3 types of quark, we could construct in different ways these particles that we were finding at our high energy accelerators. So this is how far we've come, and we are not going any further, although things do get a bit more complicated. We've gone from our atoms, where we had a nucleus and electrons swirling around it, to the nucleus, which consists of particles, protons and neutrons, and now protons and neutrons and the other particles we were finding are built up from quarks. The amazing thing is that if we just consider the world around us, everything could be built from just 4 particles. 2 types of quark, we could call the up quark and down quark. Don't blame me for these names. And the electron we've already met. And the electron neutrino, you're just going to have to forgive me if I just slide past that, because I need at least another lecture to explain what the neutrinos are. It's a very ghost-like particle. It's emitted in the burning of the sun by the billion every second. And in fact, don't start scratching. There are at least thousands of them pouring through each one of us as I'm talking. But they interact so rarely with any other type of matter. They can in fact pass through the whole Earth without interacting. So those are the 4 particles. We normally, to start constructing our new periodic table, if you like, present them like that. The 4 basic building blocks of our world are the up quark and the down quark, the neutrino and the electron. It's just sort of incredible that all the variety of the world that we see around us, the clouds and the sea and the grass and the buildings, the trees and us, can all be built up from just these 4 units. How does it go? Well, sort of working backwards, if we have a down quark and it's, I'm going forwards. If we have a down quark and a down quark and an up quark, we can build a neutron, an up quark and a down quark, and we can build a proton. I remember someone saying that it must be nice to be a proton, you have 2 ups to every down. Then with our protons and neutrons we can build nuclei. With nuclei and electrons we can make atoms. With the atoms we can make all the molecules, and the atoms make us. So from not just those 4 particles, we have our everyday world. I've specifically kept saying our everyday world rather than the universe, because again we found at our accelerators and colliding beam machines that there are more fundamental particles which are sort of equivalent to these 4 that I've just talked about. We already knew about the muon, we'd seen it in cosmic rays that shower onto the Earth. This is the other quark. I mentioned we needed 3 types of quark to build the particles that we were seeing in accelerators. So we had the up, the down and the strange were the one that we needed. In further experiments using the accelerators, the charm quark was found at Stanford and at Brookhaven on Long Island. The bottom quark and top quark were found at Fermilab near Chicago. The tau was found at Stanford. And we found that we had 3 types of neutrino linked to each of these quartets. The strange thing that we still don't understand is that these quartets, these 2 that we don't find in our everyday world, are just sort of heavier carbon copies of the 4 that we need to build the world around us. And we don't really understand that. So again, using this way of presentation that is familiar to us, particle physicists, we have our quartet, everyday world quartet, and then the higher energy quartets that come into play when we have the high energies. So they're not in our everyday world, but they're certainly in the phenomena in the universe, like exploding supernova. They were certainly around in the early days of the Big Bang and so on. Now let's look at the second question that is tackled in particle physics. What are the forces that control the behavior of those basic Lego building blocks I've just enumerated? A couple of them we're quite familiar with. Electromagnetic force, which controls all electric and magnetic phenomena. We've known about that for a couple of centuries. The gravitational force, well, we've seen that in action in the IMAX film that we've just seen. It controls the large-scale phenomena of the universe, the galaxies, planetary systems, and so on. But on the scale of what goes on in particle physics, it is so incredibly weak, a trillion times weaker than the electromagnetic force, that we just ignore it. It's vital in trying to understand what goes on in the universe at large. When we're dealing with our tiny particles, its effect is negligible. And then when we started studying the nucleus, we found two other types of force. The weak force, which controls the breakup or decay, as we call it, of particles, which is more commonly known as radioactivity, and the strong force, which holds the particles together in the nucleus. If you think about it, the nucleus has lots of protons stuffed into a tiny volume. The protons each carry a positive charge. Like two north poles of a magnet, they ought to be pushing away from one another. So there must be some force overcoming that inclination of the protons. And now this is vital to understanding the business about this new particle, the Higgs. How do those forces behave? I've taken in this little cartoon the electromagnetic force that we understand so well. How do the particles behave under the influence of the electromagnetic force? How, for example, do the electrons in the cloud around the nucleus know that the nucleus is there? If the nucleus was a mile across, the electrons would be 1,000 miles away. How on earth are they communicating? The way we now understand it is that every charged particle is constantly throwing off what we call carrier particles. In the case of the electromagnetic force, we call those carrier particles photons. And it's when another charged particle receives a photon that it's aware of the existence of the other. So that in a collection of charged particles, it's like jugglers throwing balls around, keeping them in a close cluster. They are transmitting knowledge of one another by these carrier particles called photons. And if I go back, and this is again the end of our new periodic table of fundamental particles. Here again are all the building blocks, and here are the new boys on the block, the carrier particles. The photon carries the electromagnetic charge. These three are very heavy particles, carrier particles, that carry the weak force, and the gluon carries the strong force. And here at last appears our Higgs boson. What's it there for? One of the great mysteries is, how do the particles get their mass? And the answer is that without the Higgs particle, they cannot have mass. There's a joke about, whoops, what am I doing? Press the wrong button. Who's the expert? It's the power button.
No, you're on here. I think you just, okay, listen. You may have gone.
Oh, there we go.
Okay, so which one do you want to be on?
That's the one. Okay.
All right.
There's the joke about the Higgs particle that tried to get into church, and the priest wouldn't let the Higgs particle in. And the Higgs said, "You've got to let me in, otherwise you can't have mass." I didn't invent that one either. Okay, so the mystery was, why is this one? Photon doesn't have a mass. These are very heavy. They're about 80 GeV on our scale of units. This one's half a GeV. That one's 173 GeV. Why is there this scattering of masses? We had no way of understanding it. And it was the idea of Peter Higgs. Here he is visiting the Large Hadron Collider quite recently. He's looking 50 years older now than when he had this idea about Higgs particle. He wasn't alone in having the idea. There were in fact 5 others. This is a very bad picture, but it's the only one I could get where they were all together. Their idea is not so new to us. If you think, again, you may well have played with this in your school days. You would have a magnet, a little bar magnet, you put a sheet of paper over it, you sprinkle it with iron filings, and you get these sorts of patterns. And we explain that by the fact that there is a magnetic field around the magnet that the iron filings interact with and line up like that. If you consider a compass needle in the magnetic field of the Earth, it's not really a property of the compass needle in itself that lines it up pointing north-south. It's because of the way it interacts with the magnetic field that it swings that way. If we hid it in a biscuit tin, metal biscuit tin, it could swing where it was protected from the magnetic field. It could swing anywhere. So it's the same idea with mass, namely that the particles don't of themselves have mass. It's only because of the way they interact with what we now call the Higgs field that they gain their mass. So the Higgs field, like a magnetic field, we see as existing throughout the universe. And it's carried, just as the other forces we talked about were carried by photon and so on, by the Higgs boson, which gives mass to the particles. So let me now move to more sort of practical things after that physics lecture. The amazing machine, the Large Hadron Collider, that has been built at the CERN laboratory in Geneva, Switzerland. The full title is the European Laboratory for Particle Physics. It's supported by 20 European member states, but there are some 35 other countries involved and send their scientists there to do experiments. At the moment, I think there are a good 1,000 experimentalists from the USA who do their experiments at the CERN machine. The reason being that the machine that was being built in the States at Waxahachie near Dallas was closed down after about $1 billion had been spent starting it up. About, I guess, close on 10 years ago. So in order to keep front line, the American scientists have to come to the CERN laboratory. And of course the USA therefore participates in the costs of things and in the building. Whoops, I also pressed that wrong. In the building of the Large Hadron Collider at the astronomical figure of $7 billion, the USA contributed about 700 million. Here's an aerial view of the region at CERN where the laboratory is installed, where the collider is installed. You can see it traced in this large ring. It's 17 miles around and it's built 100 yards about underground on average, so that it doesn't interfere with the activities on the surface, and it also ensures absolutely complete protection from any radioactivity that there might be down there. These other rings are just the feeders to send the protons into this 17-mile ring. Here is the main CERN laboratory, which is in the Swiss part of the site. Here's Geneva Airport over here. The Jura Mountain, this part of the ring goes under the foothills of the Jura Mountains. The frontier between France and Switzerland cuts across here. So it's the only international laboratory, to my mind, to my knowledge, that physically traverses a frontier. The ring contains about 4,600 magnets, of which the main ones are these blue cylinders here, which we call bending magnets. They're superconducting bending magnets, and they are the ones that hold the protons in the ring as they increase in energy. The others are involved in squeezing the beams when we want them to cross at the collision region. So they're traveling in here about, the beam would be about the diameter of a pencil, but when we squeeze them in the collision areas, we crowd the protons in the beam to about half the thickness of a human hair. Here is a cross-section of that complicated bending magnet. I'm sorry about you good people, you're hearing me, I don't really see anything. The actual beams travel in these two tiny apertures here. So one beam is going into the picture, the other beam is coming out. They're only about a couple of inches across. And the rest of this complicated business is concerned with keeping the magnets cold, because they're superconducting magnets. They're in fact held using supercooled helium at a temperature of 1.9 degrees above absolute zero. That's by far the largest cryogenic system in the world. The spaces within the tiny cylinders where the beams travel are pumped out so that they're very, very low vacuum. That is so that the particles in the beam aren't crashing into air molecules and getting scattered. And again, the vacuum system, it's about equivalent to pumping out the nave of a medium-sized cathedral, the amount that you have to pump out throughout the ring. The rest of it is concerned with watching how the beam is behaving so that we can control it. And of course, taking the necessary measures if the beam should go off track, because it could quite easily penetrate, burn through the vacuum vessel if we don't have it under control. It was intriguing that when we first operated this machine and the machine before it, we found we had to pay attention to what the moon was doing. So sensitive was the control of the beams that we realized, as things were going slightly wrong, that the moon, just as it pulls the sea to make tides, also pulls the earth. So that in the region of Geneva, in fact, it rises when the moon is at its closest. The earth rises by about 25 centimeters, about 8 inches. And that, because the machine was now sitting on a slightly bigger ball, it changed the total circumference of the ring by less than a tenth of an inch. But that tenth of an inch on 17 miles was enough to mess our control of the beams about slightly. This is the scheme of the crossings of the beams. So we first of all inject beams from these other machines that I pointed out earlier. Let's say in the red line, and follow the red path around the ring. When that ring is full, we switch the beams to come in on the blue line, and they follow the blue path around. When both rings are filled with protons, We power the magnets that squeeze the beams in the collision regions and collide the beams in head-on into one another in these 4 locations. The 2 that really mattered to us because of the discovery of the Higgs particle are this one up here, CMS, and this one down here, the Atlas detector. The detectors themselves, well, okay, these are some facts about the beams. When we have accelerated them to peak energy at the moment of 4 million electron volts, they're traveling as near as diameter at the speed of light. And they're going round the rings 11,000 times a second. In the collision regions, we see millions of collisions per second, usually about 6 million every second. The detectors that I'm going to show you now have about 150 million sensors, things which detect the debris coming out of these collisions. And a year's data from these sensors about the behavior of the particles would fill CDs. Someone worked this out, I didn't. Fill CDs stacking over 14 miles high in the year. It's just incredible. And to cope with that, there are about 135 computer stations, major computer stations, throughout the world in 35 countries, coping with that data. Here's an end view of one of the detectors. You could probably work out from that that they're like very large cylinders. The cylinder running out this way, this is the end piece. And this tube here coming in is where the beams will travel. They will collide in the center of the cylinder. And within the cylinder, there are sort of concentric cylinders of different type of sensors. Some of them spot the tracks of the particles that come out of the particles that collide. Some of them measure the energies of the particles. The whole thing is in a magnet, so the charged particles bend a bit so we can tell whether they're positive or negative particles, and so on. But they are incredibly complex instruments to design, build, and operate. The teams are usually usually about 2,500 physicists and engineers strong. And again, this is where the about 1,000 American scientists will be working, or have been working. The second detector that saw the Higgs is called the Atlas detector. This was the early days of the assembly. So now we're looking sort of straight down the cylinder. You can get a good idea of the scale from, here's a standard man. and all this stuff here is the stuff that picks up the tracks of the particles that emerge from the collision at the center of the detector. This one, the Atlas detector, is about 140 feet long and 85 feet high. Its magnet has more steel than the Eiffel Tower, and etc., etc. It's just an extremely large, complicated instrument to see what the collisions are producing. Here is a fairly typical reconstruction by the computers of what the detectors were seeing. The yellow lines are charged particles. The very fast ones are not being affected much by the magnetic fields, so they're emerging pretty well in straight lines. The curved ones are less energetic particles that are being bent by the magnetic field. By the way that they are being bent, we can see what charge they are carrying. The splodges of red and blue are measurements, according to their size, of the energy of the particles that pass through those particular pieces of the detector. So we're gathering a mountain of data about a collision. This is just one collision, which has to be examined to see whether there are things of interest in there. And you can sort of realize when you're looking for a couple of individual tracks in there, how difficult it is to sort them out. Looking for the Higgs, I promised no more mathematics, so I'm just going to tell you that it's quantum mechanics that lies behind all the calculations we do of this nature that tells us what to expect. It tells us that the lifetime of the Higgs before it breaks up is 10 to the minus 22 seconds. In other words, it's not the blink of an eye. And we never see the Higgs itself. We just see what it breaks up into. And here, quantum mechanics tells us several ways in which it can break up. It could break up into a couple of boson quarks. In fact, it does this most of the time. The problem with spotting that is, those quarks decay into our everyday world quarks, and they are extremely difficult to pick out because there are so many quarks pouring out of the collision. It'll also break up about a quarter of the time into a pair of these weak force carriers called W bosons, which in turn will decay into an electron, a muon, and a neutrino. And it is these that we would spot. We could spot an electron and we could spot a muon. The neutrino, however, is very difficult because, as I mentioned earlier, it just passes through everything you never see it. The only way you can get a glimpse of it is by a sort of energy balance in the collision. Has more energy gone one way than the other? In that case, maybe the other is missing energy, is being carried away by the neutrino. Things are getting more interesting, but infuriatingly enough, concerning collisions which are comparatively rare. The decay into two Z bosons, the other carrier of the weak force, is a good one for us, because electron and muon pairs, each Z decaying into either a couple of electrons or a couple of muons, we can see because we can spot those tracks. Or another way, quite rarely, 1/5%, into two photons, we can spot quite easily because the photons leave a sizable chunk of energy in a rather clean way, back to back in our detector. So this is a sort of graphic of what happens. The incoming protons here, we have to remember, they're not sort of individual point-like things. They're each a bag of 3 quarks and gluons. So it's a fairly complicated collision that's taking place. If a Higgs is produced, it's going to decay into something extremely rapidly. Here I've drawn it as decaying into 2 Z particles. They don't last very long either. We don't see them, but we do see their produce. A couple of muons and a couple of muons from each one. And we can measure the muon energy pretty clearly, and from that we can work back to what must have been the energy, or the mass if you like, because again we're changing mass into energy, of the Higgs particle. So here are a couple of things, a couple of events that the 2 detectors saw. This is the Atlas detector spotting an event with 4 muons. This was the cross-section of the computer reconstruction, and it was possible to spot very cleanly. They've obviously been coloured in a different colour now. They were yellow when we started, so we had to sift them out from the rest of the garbage that we were seeing. But and these little towers, incidentally, are measurements of energy. We could found these muons, and working back from the energy that they had we could calculate what the energy of the Higgs particle must have been from which they were produced. Similarly, the CMS detector here spotting a couple of photons. This is an end-on view. Again, lots of things that we had to pick this out of, but we were able to find quite cleanly that 2 photons had been produced. The photon energies were measured, and they gave us a measurement of the Higgs. By the middle of last year, enough information, enough data indicating the production of a Higgs, each time giving us a measurement around 125 GeV, that the teams felt confident about going public. They had incidentally been acting independently. In principle, neither of them knew what the other's data was, but I don't believe that for 1 second. So it was on the 4th of July 2012 when they felt that the probability of making a mistake with what they were saying about the Higgs particle was about 1 part in 2 million, that it was champagne time. Thank you. I'm open to questions. I know it's a fiendishly complicated subject.
Lisa Randall seems to be throwing a monkey wrench into all of this by saying that only mathematics is going to be able to identify missing forces, weak or strong or whatever. And if she's right, I think Lawrence Krauss is right, that we're all screwed.
Well, it's certainly been true in the past that when we found a mathematical way of formulating what we're seeing, so we're starting out with mathematics that's explaining what we're observing. Often by extrapolating that mathematics, thinking only of the mathematics, what the mathematics is telling us, we can predict something else, which up to that point in time we haven't seen. The most famous example of that was when antimatter was discovered in 1932. A physicist by the name of Paul Dirac had done some calculations where he was combining relativity and quantum theory, and he finished up with an equation which had the square root of a figure. Now when you've got a square root of something, let's say the square root of x squared, it could be x multiplied by x or minus x multiplied by minus x. Now x multiplied by x in this context we can understand, but not the minus x business. In fact, it indicated to Dirac that there were states of negative energy, which seemed crazy. In other words, if you push something, it would come towards you. And it was thinking about that made him predict antimatter. In other words, an electron carrying an electric charge, a negative electric charge, if we had a negative pole behind it and a positive in front, it would go that way. But its counterpart, the anti-electron, if we try to push it, it would come this way. That was the negative energy phenomenon. So the mathematics predicted antimatter, but it came from the mathematics that we had filtered out from what had already been observed. So yes, we may be leading somewhere with what we're doing at the moment, mathematically, but I'd far sooner rely on observation.
I have 2 questions. Does the Higgs boson have anything to do with like the double slit experiment, the electron, how it acts as a wave on a particle? Like, do you know, because like how electrons are double slit, if you have a stream of electrons, it acts as a wave. With the individual electron acts as a particle. And my second one was when a Higgs boson decays, that only adds up to 82%. What happens to the other 18%?
There were other modes of decay that I didn't list.
Like the strange and the charm?
Yeah, it can go in other directions.
Okay.
Quantum mechanics tells us the probability of it going in
So
particular.
if you have 2 charm quarks and strange quarks, would that make a proton?
No, but it wouldn't. It could make, I can't remember in detail, it could make one of the zoo of particles that we saw at accelerators a few decades ago. Via the business of electrons having both particle and wave, you can describe them both as particles and waves. That's true of all charged particles. In principle, it's true of the Higgs, but we've only just seen it, so I nearly said the sucker.
In science, to have a solid result, it has to be unique. Now, you were able to detect this one part in 2 million back in July, and I know that they're continuing to do more collisions and more experiments. Has it been repeated?
Yes. In fact, by now, the probability of error is about 1 in 600 million. They've now got more data, so they're extremely confident. Of course, being cautious, they always keep saying a Higgs-like. In other words, they'd really like more data about it before they jump.
Brian, this has been very interesting. Now, the application of this, because I've heard some physicists are saying this will help us identify maybe 11 more dimensions in addition to time. So what does that mean?
We don't know where this will lead. It has, however, given us our first explanation of why the particles have their particular mass. And it's like a newborn baby. You know, what's the use of a newborn baby? What it can lead to. In the past, I've been thinking about this quite a bit recently, because I've got to give another talk about where science might be headed. And when I was thinking about that, I thought, this stuff is so far from the everyday world. What use can it be? But we said 100 years ago, this is what came into my mind, concerning quantum theory, concerning general theory of relativity, so far from the everyday world, no application. In fact, our iPhones, our iPods, our television set, all our computers are all based on quantum physics. Our GPS systems are based on general relativity. If we'd stayed with Newton, we'd finish up in Tampa when we were heading to St. Petersburg, and so on. So, seemingly remote discoveries led to things which we now take for granted in our everyday lives. Where the Higgs particle will lead, I don't know. The only other thing I would add is the one area I knocked gravity off the table because it is so weak in particle. But gravity is the one force which clearly dominates in the large-scale universe that we don't really understand deeply. We can't pull it in to the quantum theory which works so well for everything else. Up to now, we've not found a way of doing it. Maybe somehow coming to know where mass comes from, which after all is the dominant way in which space-time is distorted in gravity, may lead us to a deeper understanding of gravity. A young question.
Okay. It's not a question, but a comment on it is to determine the strength of double determine the variable.
Oh, well done.
The detectors, for example, like the Atlas detector, they're very large, at least in grade. My question is, so when moons are colliding, that would be a rather manifest, but there is what would be like inside the detector?
The temperature, I cannot remember the precise figure, but it's the temperature that prevailed in the universe 1/1,000,000th of a second after the Big Bang got underway. So it's T equals 10 to the 22 centigrade or some. unbelievably. In fact, when we were launching the Large Hadron Collider project, I was asked to write a sort of popular booklet to go along with a fat, boring design document that landed on Science Minister's table. And I called that, that little pamphlet, if you like, Back to Creation, because we're really studying the extremely high energy conditions that existed in the split second after the, definitely split second, after the Big Bang creation got underway.
So to say you can violate inside that environment, you understand?
Yes.
So my question is a very different type. You mentioned miles of CDs of data and thousands of scientists, and so from the perspective of, I often collaborate with 5 or 6 people, and there's a lot of difficulty in doing that. So how is the decision made as to which specific experiments are going to be run, which computers are going to have access to which data?
By brute force.
Yeah.
No, actually, one of the, to my mind, quite amazing things about the whole CERN project is how collaboration, because of the burning interest in the science amongst those scientists, has dominated conflicts that you would expect to be there. The teams consist of Russians and Chinese and Americans and Australians and French and Germans. And they're all working together, but Israelis and Palestinians, you name it, Jordan, they're all in collaborations, but because of their interest in getting at the end product, namely pushing the frontiers of physics further out, they manage to work together. Of course, they establish a hierarchy. They have a spokesman for particular experiments. When ultimate decisions are made, they ripple up from the bottom, but eventually some tiny team, and eventually one individual, has to go one way or the other. So there is a hierarchy, but it's incredibly collaborative.
Have you had any evidence yet that these intense collisions actually are creating tiny little black holes?
Unfortunately not. There was a fear, and in fact we had to instigate an independent study, if you like, because some people maintain that those high energies, and they're correct, could potentially produce a black hole. Now a black hole is known to suck in all the matter within its so-called Schwarzschild radius. But when we knew this, but when the study was done, it was spelt out in minute detail. First of all, the energies that we are producing have in fact penetrated our world before in the high energy cosmic rays that shower on the Earth, and we're still here. If we do produce a micro black hole, it evaporates extremely quickly. Its Schwarzschild radius over which it would pull in anything is absolutely tiny, and there is a way called Hawking radiation in the computing in which the energy of that black hole can be dissipated. And the sorts of black holes that we could potentially produce with our energies are no danger to mankind, I promise.
Given that we've only really been able to unlock and explore that 15% of the metal helix, do you think that this work with the Higgs Boson will eventually enable us to go further in that direction?
It's not directly linked, other than that the quantum behavior of things ultimately dictates what is possible in DNA. DNA, the study of DNA is advancing extremely quickly in areas that had not been predicted. It was felt that there were only tiny chunks that were in fact the pieces that led to the genes, etc. We now know that what was initially called junk, quite a bit of it, is doing the job of switching these genes on and off in a way that initially was not predicted. I mean, I'm not an expert in that field, but I know there's tremendous excitement about what's going on in studies of DNA.
This is a question more about your opinion. Why was the Higgs boson particle developed out?
I think it was just because it was such a huge mystery, this business of why, that whatever solved that mystery was worthy of an almighty title. And it was the comedian, Nobel Prize winner of comedian, Leon Lederman. I could tell you jokes about Leon that go on forever.
Smart marketing. Smart marketing using the word particle.
Oh yeah, it was a nice soundbite. It was a catchy title for his book.
You started out with the equation of mass and energy, and all these studies are done just by studying energy. What is the indication that had the field or particles that gave all this energy, that created all these particles, mass? And through this, we have a new definition of mass.
No, we don't have a new definition of mass, but again, it came out of quantum theory. In particular, we couldn't understand why the carrier of the electromagnetic force and the carrier of the strong force had no mass, zero mass, and the carrier of the weak force were quite heavy particles. And it was in studying the quantum not really initially explanation, the quantum mystery of that Higgs and these 5 other characters got a formulation that eventually led them to the idea of a Higgs field and a Higgs particle. Joe, am I overrunning time?
No, you're good. The movie starts at 8 o'clock. I think if you want to answer, I know there's a few more questions, but if you want to answer them personally, I think it would be good to do that. What I want to do is just thank Professor Southworth for being here tonight. It's an incredible discussion on physics, and now I know with my memory loss I'm missing a few neutrinos. So I'm looking forward to your next discussion. Thank you, Brian. Appreciate that.